So, Jai Hind everyone. So, myself Ritesh Sharma. I am from the Electrical and Electronics Engineering Department from Ajay Kumar Garg Engineering College. So, today I am taking the topic of transformer operation at no load and on load. So, this is a very important topic of the unit number 3, where we study about the transformer actually. Okay. So, let us start with the topic. So, here you can see that we have to discuss the 3 important topics in our lecture. The first is the transformer on no load. The transformer on no load conditions. So, first we start with the, when we start with our operation of transformer, we start with the on no load condition. Okay. Then we start with the next topic is the transformer at load condition, when we apply the load on the transformer. So, how it will operate. So, it will discuss in the in this topic, and then we will discuss about the phasor diagram of the practical transformer. The practical transformer is it will contain some all the component like resistance, leakage reactance, where the losses are there. Okay. So, we are talking in terms of practical transformer. So, let us start these topics one by one. So, first we will start with the transformer on no load. In no load condition, we can say that the transformer, which is basically, we all know that the transformer is a device which is used to step up or step down the voltage actually. Okay. So, we have the 2 windings, one is called the primary winding and other is called the secondary winding. So, here with the primary winding where we connect the source actually, and in the secondary winding where the load is connected. So, suppose that if the transformer is work on our no load conditions, it means that there is a no load in the secondary side. The secondary side is almost open. Okay. Or this is the primary winding, this is the secondary winding, and the secondary winding there is a no load is connected between them. Say that the current is 0. So, this current must be equal to 0. That is I2 is equal to 0. Clear? Now, in the primary side, when we go to the primary side, we apply the voltage V1, with some magnitude and frequency. Almost we use the 50 hertz actually, 50 hertz that we are using in our system. When we apply the voltage, what happens actually? Some current will flow in the primary winding, and that current is basically very low. We call it the no load current. Is a no load current. If we assume that there is a no resistance and the leakage reactance in the winding. Okay. So, let us find out how this transformer will work actually. So, when the transformer operates at no load, the secondary windings, as I just told you, it is open circuited, which means that the no load on the secondary side of the transformer, and therefore, the current in the secondary will be 0. So, current will be 0 because there is no load, the circuit is almost open. So, in that case, what happens? The primary winding carries a small current I0, which is called the no load current, and its value is almost 2 to 10% of the full load current, or the rated value of current, you can say that. So, 2 to 10% means it is very low. If the current is 10, full load current is 10 ampere, so it is 2% or the 10%, which is quite low actually. So, this current I0 is called the no load current, which will flow through the primary winding. E1 and E2 are the 2 induced EMF in the winding, we call the primary winding and secondary winding of the transformer. So, this current, now the current is very low. So, this current is very much responsible for supplying the iron losses. Now, we know that the losses in the transformer are 2 types, iron loss and the copper loss. The iron loss basically are 2 types, hysteresis and eddy current losses, which are basically depend upon this current, no load current actually, because they are voltage dependent losses actually. So, here if the voltage is constant, because we are supplying a constant voltage V1, so these losses will be almost constant throughout the operation. So, this current is responsible for supplying the iron loss. How will I will tell you in the later, just when I will show the phasor diagram. So in the core and very small amount of copper loss. Since the copper loss is nothing but it is the I square loss. So if the current is very low, there will be no or the losses or the copper losses are almost negligible. Okay, the angle of the angle of lag depend upon the losses. Now this lag means the angle between the voltage and current, this no load current, and the voltage is totally depend upon this losses actually. Okay, the power factor is almost very low. It is almost from 0.1 to because the angle is that is quite large actually, because the windings are almost inductive. So for the purely inductive coil, it is almost 90 degree, but it is not purely. So it is almost 0.1 to 0.15. Now let us now see this the phasor diagram of the at no load condition. So in the phasor diagram, so the no load current consists of the two components. The no load current, it consists of two components. If this is the no load current, this is the power factor between the voltage and the current, that is called the no load power factor, or the angle between this voltage V1 and I0 is phi naught. So this I0 is basically consists of two components. One is called IM, the reactive or magnetizing component. IM means the component which is in the phase with this flux. So I have taken the flux phi as a reference, and we know that when there is a voltage induced in E1 and E2, they are 90 degree lag by this flux phi. Okay, as we have done in the previous classes. So this is a flux and this is the E1 and E2, which is 90 degree. This angle is 90 degrees. Okay, now from here, IM is the magnetizing component or current, or the magnetizing component of this I0 or the no load component, and IW is the working component or the core loss component. We can say that core loss component. So this current which is in the phase with the voltage is the core loss component, and the component which is in the phase with the flux is called the magnetizing component. So we have the two component called magnetizing component and the active or power component. Means this component basically is based on the or responsible for the core losses. It is also called core loss component. So one is in the phase with the voltage and other is the phase with the flux. So these two components are called the two components of the no load component. So here you can say that this no load current is equal to your IM plus IW, and these are the phasor sum, not arithmetic sum. So these are called the no load current. Now to understand the concept of a phasor, some steps, like I just told you, that the function of the magnetizing component is to produce the magnetizing flux, and thus it will be in the phase. So flux which should be in the phase, the flux should be in the phase with this IM. Okay. Second, the induced EMF, we know that the induced EMF in the primary and the secondary winding lag the flux by 90 degrees. So these are the things which we have already covered. So E1 and E2 are in phase, lag by the flux by 90 degree. The primary copper loss is neglected and the secondary copper losses are zero, because the current is zero in the secondary winding. We know that there is no current in the secondary winding, that is, there is no copper loss in the secondary winding. But as far as the primary winding, the current is very low, so we will neglect it. So there is a almost zero copper losses in the primary winding. So therefore the current I0 lag behind the voltage by, so we have seen that the current I0 is lag behind the voltage by some angle is called phi naught. We can call it phi naught, and its cosine of this is called cos of phi naught is called the no load power factor, is equal to given by no load power factor, okay, at no load conditions. Okay, so these are the some things. The active component is drawn in phase with the voltage, as I told you, and the phasor sum of this magnetizing current and the working component is the load. So this is the how. So working component, if you see this graph, this IW is in the is along with this voltage. So it is the component is called active component, and it is given by I naught cos phi naught. No load current is given by this. You can say that it's a sum of the working component and magnetizing component is called no load current. So no load current is this, and magnetizing component is Im is I naught sin phi naught. From this figure, you can see that you can calculate this value of this. So this is the I naught. So this is the active component. This is the reactive component. This, and from here you can find the cos phi, the value of cos phi. Cos phi naught is given by this. So it's very important, or it's easy to understand the some component or some to find the value of the no load power factor. How can we find the input power like this? So the no load power input, which is responsible for the core loss, is given by V1 I naught cos phi naught. Okay, so this is a conclusion which can be drawn from the this phasor diagram. Okay, so this is the concept as far as the no load transformer when we work the transformer at no load. Now let us discuss the transformer or the operation of the transformer at on no load condition. So what happens when we apply the load at the secondary side of the transformer? So the current will flow, as we can see that. Suppose this is the transformer. Okay, this is the transformer. You can see that transformer is the primary winding, secondary winding. Okay, and when the transformer is at on no load, this is open actually. Okay, now when we apply the load, okay, because this is a flux linkage, the flux is linking with the both primary and secondary winding. We call it as a phi. Okay, it is called the phi. Now when this transformer secondary is loaded, it is loaded, and suppose this is some load. The load may be at resistive, it may be inductive or capacitive. I am not talking about that. But now if the load is there, some voltage must be there and the current will be flow. Okay, now you can see that applying the right hand thumb rule, if the current is flowing, just curl your hand like this, and you apply the right hand thumb rule, you will see that the flux will go like this. This is the flux which is linking like this. The direction of flux is phi, which is constant throughout the core. When there is a load is there, the current is going like this. Okay, so it will basically what will happen? Some flux, because I2 is the current, I2 is the current flowing in the secondary winding, and then there will be a MMF is there. So MMF is how much? I2 into N2, there will be the MMF, and because of this MMF, the flux will be there, and the direction of flux is almost opposite to that of this. Suppose that the direction of flow will be your like this. And this direction like this. So it will oppose the main flux actually. So when it will oppose the main flux, what will happen? The induced EMF will be reduced actually. Okay, because the flux will reduce momentarily. It will reduce momentarily actually, so that some extra current will be drawn from the primary side, and that is called your I1 dash, which is equal to the current, the component of the secondary current at the secondary side. So now let us discuss this thing, that when the load is connected to the secondary of the transformer, the current flows in the secondary winding, and the secondary current induces the MMF called I2N2. And this force set up the flux phi 2 in this, let us call it the phi 2. Phi 2 in the transformer core, then the flux phi 2 opposes this flux called phi because of Lenz's law. Now because of this, what happens? Some extra current will flow, that is called the I1 dash into N1 because N1 is associated with this. So this I1 dash must be equal to I2 N2 to compensate that flux, because I want the flux phi constant throughout the through this operation. That means I need the phi 2 dash which is opposite to that of phi 2 so that the phi is constant. That means this current I1 dash will give you the MMF which will compensate this I2 into N2. Okay. Now let us see that. So the additional current is used to restore the original value of the flux in the core of the transformer, so that V1 is equal to I1, so that we can maintain this voltage V1 is equal to E1. Otherwise, it will change accordingly. So the primary current I1 dash is in the phase opposition with the secondary I2, so that this I1 dash value which is in the phase opposition to that of the value I2 is there of the secondary side. Thus, it is called the primary counterbalancing current. It is also called the primary counterbalancing or the primary component of the secondary. The secondary component of the primary. So from here, I1 N1 is equal to, or I1 N1 dash is equal to I2 N2. So from here, we can calculate the value of this I1 dash, which is very much dependent on the transformation ratio, which is K. So we can calculate this I1 dash is equal to K times of I2. Okay. So this is very important to calculate because the flux, we have to find the flux is constant, but momentarily what happens because of this load current, some flux will flow in the opposite. So to maintain this constant, some extra current we have to flow from the primary side. Okay. Now, so this phase difference between the V1 and I1, because now we can calculate the I1 and this I1 will be equal to the phasor sum of I0 and I1 dash. I0 means the no load component. So the phasor difference between the V1 and I1 gives the power factor angle phi 1 of the primary side of the transformer. So the phasor difference is V1 is I1 is known. So it will give you the power factor of the transformer as far as primary side. The power factor of the secondary side is depend upon the type of the load connected to the transformer, means which type of load you have connected. It is the load is resistive or it is inductive or maybe capacitive. Depending upon that, the voltage and angle, either the current will lead the voltage or the current will lag the voltage, depending upon the load actually. And if the load is inductive, as shown in the above phasor diagram, the power factor will be lagging. If the load is suppose inductive, the power factor will be lagging. Okay, and if it is capacitive, the power factor will be leading. Depending upon the load condition, we can say that the load is there. And this current I1 will be equal to given by this I0 and I1 dash in the primary. This is the primary current, which is the phasor sum of the no load current and the load component of the primary. Okay. So this is a very important concept to understand the operation of the transformer. How the transformer will behave or operate when we connect the load actually. Now let us to understand the next is the phasor diagram of the transformer. To understand the proper transformer, we have to understand the phasor diagram. How we can draw the phasor diagram means depending upon the primary and secondary or the secondary load conditions we will draw. So in this slide, the phasor diagram of this depend upon the first of all we take the inductive load. The inductive load is taken, and this inductive load means that it is we know that the current will lag the voltage by a certain angle. So suppose that we have it is the actual transformer. So we have taken the resistive or the resistance of the primary winding, leakage reactance, and similarly we have the resistance of the secondary winding and leakage reactance of the secondary. And this is a transformer core and having turns N1 and N2. Okay, and this is the primary winding V1. This is the secondary winding V2. Secondary, this is the induced EMF with the secondary winding E2, and similarly E1 is there. So let us try to understand how to draw the phasor diagram of this inductive load, transformer inductive load. Okay, so from that we can write the equations. Okay, this is the load side, this is the primary side, this is the secondary side. Secondary means the load, primary means your supplying side. So to draw the this phasor diagram, you can write down the what are the equation involved in that. Okay, so from this we can say that if you apply the KVL at this end, this E2 must be equal to, you can write down this V2, this V2, if I write this V2 will be equal to E2. E2 is a drop or the winding, induced EMF in the winding, so that is E2. Okay, minus, because this is the drop in the leakage reactance as well as in resistance. So drop in the, or current is flowing is I2. So I2 is the current plus R2 is the resistance plus JX2. R2 is the resistance of secondary winding of transformer. X2 is the leakage reactance of the secondary winding. Now this is the drop in the secondary winding. This is the J, because even the leakage reactance, the drop is almost the 90 degree like that from the resistance. And these all are the phasor sum. Okay, so this is the on the secondary side. Now come to the primary side, we know that this V1. Now V1 will be equal to, if you see that this E1 die, this E1 is nothing but the induced EMF, which is quite which is almost opposite to that of E1. So minus E1 plus I1 into, I1 means current flowing. Suppose the current is flowing is I1 and here it is I2. Okay, I1 drop in these two components, R1 plus JX1. All these are the phasor sum. Now we have these two equations on the two sides, secondary side and primary side. Now based on this, we will try to draw the phasor diagrams. Okay, based on these equations. So first of all, we have taken the flux as a reference. The flux is taken as a reference. Okay. Now E1 and E2, the induced EMF in the winding is always lag the flux by 90 degree. So E1 and E2 is taken on 90 degree of this. Okay. I naught is the no load current. Is a, since it is an inductive load, winding is inductive, so it will like something angle is, if you take it from this, the angle is almost less than 90 degree. So I naught is somewhere here. Okay, and since it is a inductive load, so voltage current will always lag the voltage by a certain angle, because since it is a, the load is given to us, so we know the power factor of that. So phi 2, if the phi 2 is the angle and the current lag the voltage by a certain angle, is called phi 2. This is the, now let us take the secondary side. So V2 is nothing, V2 is equal to E2, or you can say from here, this E2 must be equal to V2 plus I2 R2 plus JX2. So E2 will be equal to V2 plus I2 into R2. So I2 into R2 is equal to a resistive drop that will be in the phase of current. So this is the current. So this is the current I2 R2. You can see that this is the I2 R2. And I2 JX2 is the 90 degree ahead of this. So the 90 degree is somewhere like this. It is 90 degree. Okay. And if I extend this, this is my E2. So E2 must be equal to this. So this is the phasor of secondary side. Now let us come to the primary side. So we know that I1 is equal to, I1 is nothing is equal to I1 dash plus I naught, and I1 dash is equal to I2 का I2 the phase opposition of I1. So I2 phase opposition is I1 dash, and I1 dash and I2 is I1. Okay, so it should be like that, but it is slightly like so this is equal to your I1. So if you calculate the I1, which is the phasor sum of this, and then we will calculate the V1. So V1 is equal to minus E1, which is equal to V1 dash. Here it is equal to E1 or minus E1. Okay, so just minus E1 plus I1R1, and I1R1 is a phase of the, this I1R1 is in the phase of the current I1. So current I1 is this side. So in this phase, this is I1R1, and 90 degree it is I1X1. And if I join from here to here, you will get the voltage V1, because V1 is equal to this plus this. So you can see that we can draw the phasor diagram of inductive load like this in this manner. You just write the equations of the primary side and secondary side, and just draw the phasor diagram like this. So in this figure, you can see that there is all the terms. The I1 dash is opposition of the I2. It is slightly less, but it should be in the phase of this I2. So I1 dash is equal to minus of I2. So I1 dash is equal to minus of I2. Okay, because the flux or the is opposite because of this current. So this is the phasor diagram of the inductive load. Here the load was inductive. Now for the capacitive load. Okay, in capacitive load, the current is always lead the voltage by certain angle. Okay, so let first of all we understand the steps. What steps are to be followed to draw the phasor diagram at capacitive load? First we have to take this as a reference. So take the phi as a reference. If I write like this, suppose this is the phi. So taking phi as a reference. Okay. Then the second step, the induced EMF E1 and E2 drags the flux by E2. So we know that the E1 and E2 taken as a 90 degree. So let us take this as a E1 and E2. So take it as a E2, E1. So they are 90 degree. Okay. So as we know that the load is capacitive, so there is an angle between the voltage and current is this, and such that the current is always lead the voltage. If this is the voltage, so current will be like this, I2. So this the current is always leading by a certain angle. Maybe it is phi 2. Okay. So the component of the applied voltage in the primary equal to the opposite of the induced EMF. Okay. Let us see that. Now next is the current component of the current. Now we have a no load current. So let us draw the no load current like this. If it is a no load current, okay, we know the no load component of the current is this, and since we have the I2, so I2 dash, this is my I2 dash. Sorry, not I2 dash, it's I1 dash. It's I1 dash. So it's I1, since it is a primary component. So I2 phase opposition is I1 dash. I1 dash and I naught. Since E1, I have taken that the E1, I minus E1. So means phase opposition of that. So minus E1 is this. So minus E1 is something like this. Minus E1. Okay, if it is even, so it's minus even, or it's like minus of even is this. Now find the first the what is the value of current I1. So I1 is, we know that the I1 is equal to the primary current is equal to I0 plus I1 dash. I0 plus I1 dash. So you can draw the phasor sum of that. So this is my I1. Okay, this is my I1. And now I will calculate the value of V1. So V1 must be equal to how much? Minus E1 plus I1 R1. So I1 R1 in the face of this. So I1 R1, I will take another color. Let us take the green color. So this is the face of I1. So this is my I1 R1. I1 and R1. Now let's say I1 X1, which is 90 degree of that. I1 X1. And now if I join this from here, this must be equal to my V1. So V1 here, it will be equal to minus of E1 plus current is I1 R1 plus JX1. And here V2 is equal to, we know that the E2, sorry, E2 will be equal to V2 plus I2 R2 plus JX2. So if I2 is this, V2 is this, so you can say this will be your I2 R2. So I2 into R2 in the phase of this. So this is my I2 R2. Not like this, just 90 degree of this. So in 90 degree, like this. So it will be like here, somewhere here. So wherever it will cut to this will be my E2. So E2 must be equal to V2 plus I2 into R2. So these two equations will justify from this. This is the basically the phasor diagram for capacitive load. Here I1 is lead the voltage by V2 by some angle called phi 2. Okay, so you can note down these steps to draw the phasor diagram. So where V2 is the call E2 minus whatever voltage drop is there, which is in the I2 R2 plus JX2, and I2 R2 is in phase with the current, and I2 X2 is in the quadrature with the I2. So these are the some steps which you can remember, so that we can find the, or we can draw the phasor diagram as far as the capacitive or inductive load. For resistive load, we know that the voltage and current in the same phase. The load is resistive means the voltage and current in the same phase. Power factor is unity. So we can also draw it further. It is quite easier. Okay. So that's why I am taken the two cases of inductive load as well as capacitive load. Okay. So this is how we can draw it. So this is very important topic to understand the concept of transformer at no load and full load actually. Okay. So thank you so much. So that we will meet in the next lecture. Thank you.